In the last section, we talked about a technique of solving differential equations called separation of variables, and that technique went something like this. We rewrite, and we were just using the notation that y prime is dy over dx, just as a handy kind of notation. And then we put all things in the problem having to do with y on one side, all things having to do with x on the other side, fundamentally. And so in this problem, I would multiply on both sides by dx. I would divide on both sides by 1 plus y. So we'd have this. I would probably rewrite this as 1 over 1 plus y dy, kind of separating for integration purposes, and then we would go about the integration process. But I want you to notice that the first order of business in this separation of variables idea is to rewrite our equation in this kind of form. Now, even more generally than what I have right here, the really general idea of this is that we have a function in terms of y dy and a function in terms of x dx. And if we can accomplish that form, we can use the technique. And there are other variations of this general idea. One of them, I think this is the one that is shown in your textbook, but if you can manipulate into any of these forms, then you can use that method. Let's use the method on this problem. Now, this is a little bit more sophisticated maybe than the ones that we have faced in the past, but we begin the same way. We think of y prime as dy over dx. All right, now I want to sort of separate this dx. I want to multiply on both sides, so it makes its appearance as a factor over here. Now I want to separate the y's and x's. You see, I want dy here. I want dx over here. I want all the y information over here, all the x information over there. Okay, that's really all there is to it. I'm dividing on both sides by x squared plus 4, so I get x squared plus 4 in this denominator. I'm dividing on both sides by y, so I get y in this denominator. And I'd like to go through the separation process here and the separation process here. And now I'm ready to integrate on both sides. So I show integration on both sides, and away we go. Now, I do notice that over here, to integrate, I want the y prime over y form. And the y prime, if this is the y prime would be 2x. So I need a 2 factor up here. So I do the 1/2 and the 2. In this form. And now I'm ready to go. This becomes the integral of 1 over y is ln absolute y, and on the right I have 1/2 ln denominator, which is 1/2 ln x squared plus 4, and then plus a constant. And then I go through a manipulative process to solve this for y. Well, the 1/2 here can be thought of as this is natural log of this to the 1/2 power, or it's natural log of the square root of x squared plus 4. All right, that's a way to do this. Now, at this point, we can go directly into the exponential form, or we can continue to manipulate. I'll tell you about the continued manipulation in just a minute. But if we go into the exponential form, it is base exponent equals absolute y. So absolute y is equal to e to this exponent. All right, now we have seen the manipulation before about this business. The e to the c sub 1 power is one factor here, and e to this natural log is the other factor here. And the e to the ln, some number, remember when e and ln are right here, all this is just that number. So that's why I brought this down. Now, the absolute value is plus or minus all of this. So y is plus or minus all of this. And because of the nature of our problem, this can be thought of as simply c. So we can manipulate to this form. Now, up here I mentioned that we could continue the manipulation process. We can actually put all of the terms in an equation like this having to do with logarithm on one side, and then manipulate using the properties of logarithms. For example, here, this could be thought of as ln absolute y minus ln root. And then we would have ln absolute y over the square root of x squared plus 4. And then from there, go into the exponential form. So either way, though, it all comes out in the wash and we get the same result. Suppose we want to find the equation of the curve that passes through the point 1, 3. with slope y over x squared at every point xy. The flow of this problem is that we're going to write a differential equation, we're going to solve the differential equation, and we'll have a general solution. And then, using the information about the curve passing through the point 1, 3, we will go to a particular solution. Here's how it flows. Now, when we see that this curve has a slope of y over x squared at every point xy, that should bring up the notion of derivative. So y prime then is y over x squared. All right, and now we want to solve this. So we'll use separation of variables. We're writing y prime as dy over dx. And now I kind of swap these two to put all matters involving y on one side, all matters involving x on the other side. I'm dividing both sides by y, multiplying on both sides by dx. So I get dy over y dx over x squared. And the integral then of 1 over y dy is equal to the integral of x to the negative 2 dx, and that gives us the natural log of y equals x to the negative 1 over negative 1 plus a constant. And now it's just a matter of cleaning up pretty much. We can rewrite like this and then go to the exponential form. This is y equals base to this exponent. And now, you remember, I'm sort of skipping a couple of steps here, but we've seen it so many times before. It's e to this exponent, and each of these actually is an exponent on e. And the e to the c1 we'll think of as the coefficient of e to the negative 1 over x. So we have ce to the negative 1 over x as the general solution to the differential equation. Now we use the information that the graph passes through the point 1, 3 to go to a particular solution. So we'll take this form, and up here, if the graph goes through 1, 3, then here's our form, and x is replaced with 1. So we have negative 1 over 1, or negative 1, and y is replaced with 3. And what we're doing here is solving this for c to give us that particular equation. All right, so let's see, this is 1 over e, multiply on both sides by e, we find c to be 3e. If c is 3e, we're replacing back into this form, replace c with 3e, and we have this, and then e times e to the negative 1 over x can be manipulated in a few different ways. One way is just to say it's e to the negative 1 over x plus 1, or e to the x minus 1 over x. And if you look at the graph of this on your calculator, you'll find that the graph does indeed go through the point 1, 3. Well, not all differential equations can be solved using the method of separation of variables. Here is one such differential equation. Now, if you try to attack this one and solve it using separation of variables, you would paint yourself into a mathematical corner fairly quickly. You might try it. But there is a technique that we can bring to bear on this equation and others like it. And I'll tell you what characterizes this equation and the family of equations that we can apply this technique to. But the technique involves this. We are going to make a substitution here, and then we're going to separate variables, and it'll be successful. We're going to let y be substituted. We're going to substitute vx for y. So y equals vx. Now, if y is vx, then y prime is v plus x times the derivative of v with respect to x. All right, so we're using the product rule, we get this. Now, with that in mind, we make the substitution of these two back into the original. So the y prime, this, is that, and I brought it down here. And the y that appears here, we'll substitute vx for that. And now we'll manipulate a bit. And the manipulation in problems like this can get a little bit challenging, but because it is challenging, we just need to keep track of things and write very legibly and try to do one or two things at a time from step to step. Just don't get too far ahead of ourselves. Well, let's see. Over here, I'm noticing that we have x factors in the numerator, in both parts of the numerator, so this x cancels with both of those, leaving 3 plus 2v. I notice that we have a v here and 2v over here. If we subtract v on both sides, it gives us this single v on the right. Then if I multiply both sides by the dx, it goes out of this side leaving x dv, and on the right we have dx times the v plus 3. Now I'd like to separate variables. I'd like to put all matters involving v on one side, all matters involving x on the other side. So I'm going to take this x and divide on both sides, and it'll make its appearance in this denominator. I'll divide on both sides by v plus 3, and it'll make its appearance in this denominator. Now I'm ready to go. You know, this is 1 over v plus 3 times dv, and this is 1 over x dx. So I take the integral on both sides, and take the integral here, and I get the natural log of v plus 3, and the integral here gives the natural log of x, plus a constant. And now I go through as I normally would. There are several ways to manipulate from here. I mentioned this technique a little while ago, and I want to show it to you here. I'm going to subtract natural log on both sides. You see, one way to do it from here is to say, okay, let's directly go into the exponential form. So we would have v plus 3 equals e to this exponent. Well, the other way to proceed is to subtract ln x on both sides, and now we can consolidate these two as the natural log of one entity. So it's the natural log of v plus 3, and the minus means divide, so it's v plus 3 divided by x is what we have on the left. And now we go into the exponential form, and it's this is equal to e to the c sub 1. And e to the c sub 1, that's c. And multiplying on both sides, we have v plus 3 equals cx. And the v, we'll back substitute now to get into the xy idea. So v, well, let's come back up here and let's make sure you understand what I'm doing here. This y equals vx. V, then, is y over x. All right, so we're back substituting using this idea. All right, so the v is y over x, and then multiplying through by the x, we get plus 3x and then cx squared, and subtract the cx on both sides, and we get this. And there is some latitude here. I want to show you another technique, just kind of a mathematical trick that we could use here to make things even faster. Now, you know what I did is I subtracted natural log on both sides. Another way to proceed right here is, instead of writing c subscript 1, I'm going to write a constant in another form, a form that's more compatible with, more convenient for what I'm seeing here. I'm seeing natural log in all matters except this one. So why don't we use a technique where, instead of writing c subscript 1, I think of this as the natural log of c. You see, the natural log of c, that's still a constant. Now, we're not going to belabor the issue of positiveness and negativeness and all of that kind of thing. That kind of comes out in the wash. Let's just look at the technique and not worry about that for right now. So, let's see, we have natural log x plus natural log c. Well, we can consolidate those two because the sum of two separate logs at the same base is the logarithm of their product. So we have the natural log of cx. Now on the left we have the natural log of this expression. So notice we have natural log on both sides. So we can undo that natural log on both sides, and we get v plus 3 equals cx. A nice clean little method for getting to this point in our problem. And then the rest of it is the same as it was before. V is substituted back for the y over x, multiply through by x, and we find y to be cx squared minus 3x. Now it turns out that we can check this solution by going through a process that looks like this. Our solution is this, or we might say, gee, our candidate for a solution is this. So it's y equals cx squared minus 3x. So the derivative of that is 2cx minus 3. Now with these two equations, we can put them into our original differential equation, which is this. Substitute these two in here and see if we have truth. That is truly the essence of the notion of solution, isn't it? So the y prime is the 2cx minus 3, and the y is cx squared minus 3x. Okay, so we set these two equal to each other, and notice the y, I'm substituting the cx squared minus 3x. And then manipulate this a bit, and it'll drop down to 2cx minus 3 equals 2cx minus 3. We have truth, so we do indeed have a solution to the differential equation. The differential equation we just looked at and applied this technique of substitution to belongs to a certain family of functions. They're called homogeneous functions or homogeneous differential equations. And we need to be able to recognize those if we're going to be able to tell whether or not this technique is going to work on a particular function. Well, homogeneous differential equations or homogeneous functions are functions that are of the form y prime equals f of xy. Actually, I don't need the y prime, but if we're talking general functions, you see, and we want to put them into this category of being homogeneous, then we would just use functions of the form f of xy. Now, we're thinking of identifying homogeneous differential equations, and that's why I'm using the notation here. All right, so y prime is a function of the form f of xy. All right, a function in two variables. So this isn't too scary for us. But these rascals are homogeneous differential equations if f of tx ty is equal to t to the n power times f of xy. Now this looks kind of funny, but all it means is that we take the x's and y's that appear in our function and replace with tx and ty's, and then we try to factor the t out. You see, we try to yank those t's out, and if we can write it in this kind of form, then we have ourselves a homogeneous differential equation or a homogeneous function. Now the n here in the t to the n is the degree of that function. And if we try to apply the idea to the function that we were talking about a while ago, we had a y prime, which is f in terms of x and y, and it was this. Now, what does f of tx ty mean? Well, it means in the f function, replace x with tx and y with ty. You see, replace these with those things. And when we do that, it's pretty easy to see that we can snag out the t in both numerator and denominator, so we have t over t, which we can write as t to the 0 power times f of xy, times our expression that we had before. This is kind of a trivial version of a homogeneous differential equation, but it's useful for us to see that it falls into that category because of this technique. Here's another one that represents perhaps a little more imposing, a little more representative of the idea of a homogeneous function. This is f in terms of x and y, so it's a function written in terms of variables x and y. All right, what is f of tx ty? Well, replace x with tx, replace x with tx, replace y with ty, replace y with ty. Now, expand a little bit and let the smoke clear and then factor. Here we have tx to the third power cubed is t cubed x cubed. Here, t squared times t is t cubed, x times y squared is xy squared. And then t cubed y cubed for this one. Now, notice that t cubed appears in all three of the terms, and so we snag out that t cubed, and we have t cubed times this expression, but this expression is the expression we started with, and so this is t cubed times f of xy. So we have a third degree homogeneous function. So here's how we can recognize those things and apply this idea of the substitution in order to separate the variables. Well, a rather intriguing topic appears at the end of this chapter, and it's a topic that is entitled orthogonal trajectories. And the word orthogonal it's kind of a fancy word that means perpendicular. And you know, if we think about a general equation or a general function, and general in that it falls into a family. There's a family of functions here. And the family, it manifests itself with a constant somewhere. And so you have a constant. The constant can take on various values, and therefore the graphs can take on different forms. I shouldn't say different forms. They can appear in different places, but they sort of have the same form. They sort of have the same kind of curve, but they're just a little different from one another because of the constant. And these things can have some really interesting configurations by just changing the value of a c in some kind of relationship involving x and y. All right, now the orthogonal idea is that you have a whole family of functions and their graphs, and we want another family whose graphs are everywhere perpendicular to the graphs of the others. That is, everywhere they cross, they're perpendicular. Interesting idea, but not too difficult to understand conceptually from what we already have at our disposal. You have a family of functions, okay, and you've got this function describing the family that involves a c. Okay, fine. And they have graphs. Okay, fine. So you take the derivative of that first family of functions. You got your derivative, and now the derivative talks about or addresses the idea of slope. Okay, now you change that, the slope idea. Remember, perpendicular slopes have the characteristic that they are negative reciprocals of one another. So you take this slope idea and generate the negative reciprocal, and then go back using differential equations to a new family of functions, and bam, you have a whole family of functions that are orthogonal to the original family. Now, this situation, it sounds really amazing, but it applies in areas of electrostatics, thermodynamics, hydrodynamics. And you can read about these a little bit in your textbook. I'll let you do that on your own. But I want to show you how the technique runs, and I'll just show it to you rather quickly. If you start out with a family of functions that's y equals c over x, all right, the technique involves derivative. Now, before you take derivative, you solve this for c. You want to isolate c. That's just part of the technique. So you solve it for c, and now we're going to differentiate implicitly. And to do that, now we're using the product rule here. So it's x times the derivative of y plus y times the derivative of x. And we're implicitly differentiating in terms of x. All right, and then the derivative of the constant is 0. Okay, now we'll solve this for y prime. Kick the y to the other side, divide on both sides by x, we have this. So y prime is negative y over x. Now this is the slope of the given family of functions. Now, to think about the slope of the orthogonal family, you think about the negative reciprocal of these. The negative reciprocal, the negative, change the sign, flip over, we have x over y. So here we have the slope of the orthogonal family. Now, what is that orthogonal family? Well, this is a differential equation, and we can find that family of functions rather easily. Now, this is dy over dx, and let's pick it up here. dy over dx is x over y with, let's see, the y goes over here, the dx goes over here. We're just cross multiplying, so we have this. And we take the integral on both sides. We find y squared over 2 equals x squared over 2 plus a constant. Now, this particular one lends itself to a form which is rather familiar to us from college algebra. If we move this term to the other side, then we would have this. And it's beginning to shape up, you see, as the equation corresponding to a hyperbola. And it will if we can make this appear to be 1. And we can do that by multiplying on both sides by 1 over c sub 1. So we do that here, we do that here, times both parts. And now these denominators would become 2c sub 1, and over here we would have 1. And these 2c sub 1 denominators we can write simply as a constant, c or k or whatever we would like. But here's the form then of the family of orthogonal functions, orthogonal trajectories. Even though there's a graph of the two families of functions in your textbook, I was kind of curious about how they would come up on the calculator, and I'd like to share that with you. We're going to take a look at the first family of functions, the family that is y equals c over x. And notice that I'm using a positive value of c for all three of these. And here's what those graphs look like. Now notice that they only appear in two quadrants. Well, let's go back and add. I'm selecting the next several here, Now notice the value of C is negative for all three of these, and the graphs then look like this. Okay, so we have all of these graphs. These are all members of that family of functions that are of the form y equals c over x. Now, we want the orthogonal family, and in order to enter these on the calculator, we have to first solve for y. And in solving for y, just as we found with hyperbolas before, we get situations where we've got a plus or minus the square root of some expression. So this is plus and this is minus the square root, and the expressions are the same for these two. Now the c is found in this expression. It's not easily seen as it was before, but this is the c and that's the c. The leading one here and this one. If you'll solve the family for y, you'll find out that these are the positions for the c value. Now, just for this particular item, I'm going to select these two equations and take a look at the graphs of those two. Okay, so we have a hyperbola situation like this. These are the wings of the hyperbola, and notice perhaps not obvious, but the apparent perpendicularity among the graphs of the two families of functions here, and that's what we would expect in this situation. Now, I don't have a lot of latitude in selection of additional functions here because I've only got 10 to deal with, 10 possibilities here on the TI-83, but I will show you a couple of them where the c value is negative. Now here's the c value, negative c value occurs in these two positions. And when I entered y subscript 10, the 10th function here, I just made it the negative of the 9th function because these are just negatives of one another. And the graphs look like this. They're the ones that kind of oppose the others in this other direction. We have a horizontal transverse axis here, but at any rate, now notice also that the graph doesn't appear right through here, and that's just because the function is not defined. It's apparently for some x value that is irrational. We have a crossing of the x-axis, so that's why no appearance of the graph right here. But at any rate, we're seeing the idea of the two orthogonal families here. A rather interesting concept, isn't it?